Hi and welcome. My name's Michael, and in this lesson, we're going to be looking at network traffic. Now that we're familiar with the basic components that make up a network, that is NICs, switches, and routers, we can talk about how the data moves through the network. Let's get started. So I'm here on the second section on the left, network traffic within the interactive diagram. And the first portion of this section is going to be network traffic methods. And so here we have our small network that we looked at in the last lesson, and we're going to talk about the three ways traffic can move through the network. The first method, the most common, is unicast. Unicast is one-to-one. That is, one device on the network sending traffic to one other device on the network. Now, for the purposes of network topology, switches don't really count. They just forward the packets on. They're not a destination. So in this example, the green computer here on the left is sending data through the switch to the orange computer here at the bottom. That's unicast, one-to-one. Again, that's the most common method of traffic. Another method is multicast. This is one-to-several or one-to-many. So in this example, the green computer is sending data at the same time to these three computers, the three orange computers at the bottom. And the reason you might do this would be you have a server farm and they're keeping each other up to date, and they're doing so through multicasting. Now, if we follow this kind of as a thought experiment, we'll see there's going to be a lot of crosstalk. If every computer is multicasting to every other one, then it's going to exponentially grow and we're going to saturate our network, and that could become a problem. But there are valid use cases for multicast. The last form of traffic is broadcast, and this is one-to-all. So this is our green computer here on the left is sending out traffic to every computer on the LAN, or every device on the LAN, every destination. And because our router is part of our LAN, it is also receiving that data. Now, why would a computer do this? We'll talk about that when we look at addressing and get into ARP. So let's talk about the OSI layers. I don't want to spend a ton of time on OSI layers. They're an important abstraction model, and it's important to understand them. But in the context of subnetting, you just really have to have some exposure to them. You don't need to have a complete and thorough understanding of the OSI layers. Just know that the OSI layers are an abstraction model that all network traffic follows or passes through. And so traffic would begin at the application layer, and I've kind of condensed 5 through 7 since this is all managed by the application. So it starts at the application layer, it moves down through the transport layer, down through the network layer, down through the data link layer, across the physical layer, and then it comes back up through the physical, through the data, through the network, through the transport, and into the application on the other side. So let's look at the application layer, and I've condensed layers 5 through 7 again, the application presentation and session layers. These are typically managed by the application itself, and they provide the interface for the user to communicate. The data being passed at the application layer is user data. And so a real-life example of this would be a web browser. It is the application that you are using to interface with, and the data is kind of being managed by the application. So if you're watching this video on the internet, your web browser is managing that. It is managing it, the application, the presentation, the session layer. A more conceptual example, and probably one of the best ways I've ever seen this explained, was ordering a pizza for dinner. The application layer is the phone that you use to place the order. It is the user interface that you're using to place the order. The presentation layer is the fact that you both need to be speaking the same language. So you're speaking English, and you call and the pizza store answers. They're speaking English. You're both able to have that conversation. That's kind of the abstraction of the presentation layer. And then for the session layer, the person that you're calling, the pizza store, has to answer. There has to be someone on the other end that says hello. So moving down into the transport layer defines how data will be sent. It provides validation and security, and the data being passed at this layer is segments. That includes the user data chunked into segments. This is the layer where firewalling occurs, if you're familiar with a firewall. A conceptual example, again, so you've called the store, you've ordered the pizza, This is where QA gets involved, and they make sure that only the pizza that you have ordered, only the toppings that you want go on that pizza, and that you don't get the wrong pizza. Next, we have the network layer. This is layer 3. And this handles routing the packets across the network through the best route to reach the destination based on your IP address. Again, we're going to talk about addressing coming up. Just know that IP addresses are sources and destinations on the network layer. In our conceptual example, the pizza store is going to use GPS to find the best route to your house. Next, we have the data link layer. This is layer 2. The data link layer handles communication between adjacent network nodes via the physical addressing, MAC addresses. Again, we'll get into that when we talk about addressing. Just know that IP addresses for layer 3, MAC addresses for layer 2. For our conceptual example, the pizza store needs your full address. It needs to know right down to the house number where that pizza is going. And then lastly, we have the physical layer. This is the physical bit level transmission layer. So this is the wire from your NIC to your destination. It could be radio waves, it could be fiber with pulses of light. But this is the physical connectivity. In our conceptual example, you've ordered the pizza, they've made the right pizza, they've got the address to your house, they've got the full address to where to take it. This is the roads they're going to drive on to get that pizza delivered. So that's the OSI model, and if you do any work with networking, you're going to become relatively familiar with layer 2, layer 3, and layer 4. Layer 4 is going to be the port-to-port transmission. Layer 3 is going to be IP address to IP address transmission, and layer 2 is going to be MAC address to MAC address transmission. So let's look at the actual data. So here we have a TCP IP example. We have our application layer here. We have our transport layer here, network layer here, data link layer here. So looking at the application layer, your application is going to create some data, some user data. By virtue of you interacting with it and it making network calls, it's going to assemble maybe web requests. It could be a form you're posting, something like that. It will have its own data set that it is transmitting across the wire. This is the whole point of having the network, is this data here, the user data moving back and forth. A lot of times the application itself will put an application header in front of that data so that the application on the receiving side has some context with what to do with it. So the application is going to create some user data, and then the application is going to put a little header in front of it. Now, as that data moves down into the transport layer, layer 4, in the TCP IP example, now we could be using UDP, but that's just kind of an unverified stream of data. There are other protocols as well, but TCP is the most common and a good fit for our example here. A TCP header is going to be placed in front of this. One other thing, this is going to be referred to as a segment. So at the transport layer, you have segments. At the network layer, you have packets. And at the data link layer, you have frames in the Ethernet example. So the transport layer is going to have a TCP header, and the data in this header is going to be the source port and the destination port. So if you're making a request over the web, your source port may be something high and unprivileged, so port 65,000 something. But your destination port is probably going to be port 80 or 443 at your destination. That would be HTTP or HTTPS. So a regular website or an SSL site. Some additional data is going to be sent, like the sequence number, the acknowledgement number, data offset, reserved, control flags, window size, checksum, and urgent pointer. The checksum is notable because this is the mathematical hash that will be used to make sure that the segment integrity has not been compromised. If it has, it can request a retransmission. Moving down into the network layer, we're going to have an IP header preceding the packet. So the packet is going to contain segment data, application data, user data. So the IP header is going to be looking at the source IP address and destination IP address. And you can see there's a lot of other information contained in the IP header, and a lot of this is to facilitate smooth transmission. Again, we have a checksum to verify integrity. We have a time to live, so how long it can exist on the network. the protocol, which version of IP are we using, some basic environmental data, version and length, and then we have options and padding to make sure the math all works out in terms of how many bits everything is. Moving down into the data link layer, we now have an Ethernet frame. And so the frame data is going to include packet IP data, segment application data, and of course the user data. One thing to keep in mind is that each one of these frame, packet, segment, so forth, have different maximum and minimum sizes. So think of them in relation to one another. The lower layer dictates the maximum size of the data that can be handled from the layer above. One difference of the frame is that the frame is going to have a header and a footer. So think of it as a frame around a painting. It completely encapsulates the frame data. So looking at the frame header, we're going destination address, MAC address, and source address, MAC address. TCP header was port to port. IP header is IP address to IP address. The frame header is MAC address to MAC address. So looking back at that, with a preamble, which will synchronize where the frame starts, we have our destination address, a source address, the length and type, all of that packet data, and then the frame check sequence, which is a lot like the checksum for the other two headers, and is used to detect compromised or corrupt frames. So the term packet is a little loaded. Let me talk about the semantics of that real quick. The Ethernet protocol on the physical layer, layer 1, the unit of data is often called an Ethernet packet, which has an Ethernet frame, that's layer 2 here, as its payload. But the unit of data of the network layer 3 is also referred to as a packet. So you hear the word packet used in a couple of different contexts. Another semantical difference between the packet and the frame is that the frame envelops the payload with a header and a trailer, like I said. So now we know the basic components of networking, and we have a pretty good understanding of how that data moves through the network. We're in a good position to actually talk about subnetting, why we do it, how we can start doing it, and things of that nature. This lesson is now complete. Thanks for watching.